This is question 2 on chemistry from section 2 of the 2020 BMAT. So we're told that a particular element has 2 isotopes, and they're given in this table, which includes the numbers of protons, neutrons and electrons, and the relative abundance of each of these 2 isotopes. And so we're asked, based on this table, what is the relative atomic mass of this element sample? And the answers are given to 1 decimal place. So firstly, if we're dealing with the relative atomic mass, what is that exactly that we're dealing with? So the relative atomic mass is the average mass of a sample based on a weighted average of the 2 isotopes. So we need to take into account the masses of both of these and include these relative abundances in our calculation. And so which parts of the atom do we need to include in this mass? So we know that protons and neutrons are much heavier than electrons, and so we can consider the mass of the electron to be negligible in this problem. So we just need to worry about the protons and neutrons, P and N. So let's set up a quick column in this table to work out the total number of protons and neutrons. They, of course, both weigh approximately the same, and they both weigh 1 unit in terms of the relative atomic mass units. So we're simply adding 31 and 38 for this one. That takes us to 69, and 31 plus 40 for the second isotope, which takes us to 71. So that is the mass of each of these 2 isotopes, but we're interested in the average of these 2 based on these relative abundances. So how do we go about that? Well, how do we work out a weighted average in general? So we multiply the abundance by the number. So if we multiply 60% by 69 mass units, so AR is our relative atomic mass, and we add to that the abundance of the second one times its mass. And then what do we divide by? So we've got 100 percentage units total, so we're dividing this sum by 100 to get our average. Now, this looks like it might take us a while, so maybe there's a quicker way of going about this. So if you think about it, we're just interested in the number which we know will lie somewhere in between these. These numbers have a difference of 2 between them, but would it matter if these numbers were much smaller, such as 1 and 3? Well, no, because the number that would lie between them, the appropriate distance to each of the 2 numbers, would be the same, just with the difference that we choose between this pair of numbers and the ones that we choose. So in other words, if we do a quick shortcut by doing this sum, but just with the numbers 1 and 3, for example, because the maths would be much easier. So 60 times 1 plus 40 times 3, well, that's 60 plus 120, which is 180, and 180 divided by 100 is 1.8. And so how has this helped us? Well, we know that the weighted average of 1 and 3 would be 1.8. And so if we apply that logic to this problem on the left, where we have 69 and 71, we can see the difference between the lower number and the average is 0.8. So we're just adding 0.8 to 69. So we know, based on our reasoning in this right-hand argument, that because the difference between the 2 numbers is the same, we can apply this logic to our first problem. And so we've saved ourselves timesing 69 by 60 and 71 by 40, which might have taken a while, but we know that this is our correct answer. And so 69.8 is our relative atomic mass, which corresponds to an answer of E.